Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we explore the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Well, let's move right along and take the first listener phone call.
Steve Winters, Las Vegas, Nevada. If a star 500 billion light years away went supernova and we were just looking up at the sky at the right time to when that light was reaching us, would we see the explosion or would we just see the star extinguish and go dark? Thank you.
Well, first of all, if a star is 1 light year away from us, it'll take a year for light to reach us. So if a star is, let's say, 500 million light years from Earth, and we see the explosion, then it exploded 500 million years ago. So the night sky is a time machine. You're not looking at the night sky as it is. You're looking at the night sky as it was. Now, what will you see? Well, first, you will see the explosion. You'll see a gigantic fireball. And out of the fireball, when it starts to condense, then at the very center of the fireball, you may see a neutron star, a star which is the remnant of the supernova explosion. A neutron star, by the way, weighs about as much as the sun, in fact, if not more, but size-wise, it's the size of the Earth. So after this titanic explosion called a supernova, you get a tiny little remnant, the corpse of the original star. And if you take a teaspoon of it, a teaspoon of white dwarf material will weigh as much as a mountaintop. And so just remember that what we see in the cosmos is not what is actually there. When you look at yourself in the mirror, for example, you're actually seeing yourself a billionth of a second ago. Because it takes about a billionth of a second from light to go from your face to a mirror back to your eye. And then the question is, of what use is this? Well, we use supernovae as a standard candle in which to judge distances. A star that is very close to us looks very similar to a very bright star that is very far from us. And so it's hard to tell the difference between a close star that is dim and a far star that is quite bright. That's why we need a standard candle. And there's a certain type of supernova type 1A, that is the standard candle. So this discussion is not academic at all. This is how we measure the size of the universe. Okay, well, let's move right along to the next listener phone call.
Hi, my name is Ronald Price from Louisville, Kentucky. My question is, it's kind of long, so bear with me. I've believed for many years that it would be possible to migrate the Earth away from the Sun when needed in the next couple billion years when necessary. Since the Moon has no atmosphere, it's no different than a giant spacecraft that can be manipulated with rockets mounted to its surface or attached to stilts, where the rocket exhaust is far enough away to not create an atmosphere on the Moon. I was taught long ago if the Moon wasn't revolving around the Earth due to momentum, the Moon would fall towards the Earth. If we kept the Moon from falling towards the Earth would then fall towards the Moon. However, if we kept the Earth and the Moon at the same distance from each other, the Earth will migrate towards any direction the Moon is pulling it in. Thus, at the right trajectory, we could migrate the Earth away from the Sun and, theoretically, take the Earth with us anywhere we want to go without the need to abandon it. Will it be possible to migrate the Earth anywhere we want to go with the advanced technology obtained in the next couple billion years? Thank you very much.
Well, at first your question sounds preposterous. However, serious astronomers have actually looked into that very question. You see, 5 billion years from now, the Sun is going to eat up the Earth. The Sun will devour the planet Earth, and all life will be extinguished. Therefore, some people have advocated moving the Earth Now, the moon, it turns out, does not have enough energy to draw the Earth away from the sun. Plus, you have to move the moon, which, of course, is in itself a very big task. However, we have asteroids. Asteroids from a very far distance. It wouldn't take much to nudge an asteroid so that it comes whizzing by the Earth and executes a slingshot maneuver. And because the asteroid whips around the Earth, it actually pushes the Earth away from the sun as a consequence. Now, if you do the math, you can show that the moon is not big enough, not suitable enough, not fast enough. But asteroids whizzing through outer space may do the trick. You have to have a lot of them. You have to synchronize them just right. But, hey, billions of years from now, we may have no choice. Either we leave the Earth or we move the Earth. Welcome back to Science Fantastic. And once again, this hour is your hour. Okay, let's move right along now to the next listener phone call.
Hi, my name is Justin, and I live in Oxnard, California. And I have a question about full immersion virtual reality. Do you think full immersion virtual reality is going to have a big impact in mental health in the future and tourism? Thanks.
Well, you ask a very interesting question. Full immersion virtual reality is when you create an imaginary world, partly by putting on goggles, but also perhaps sending messages directly into the brain itself, creating memories that weren't there before. Now, we can't do that yet. We have virtual reality goggles, of course. But if you go to my book, The Future of the Mind, you realize that, yes, in the future, we may shoot memories directly into the brain itself. Now, what does this have to do with mental health? First of all, many people take drugs because of the harshness of reality. They want to escape. And, of course, the problem is drugs are addictive. Well, virtual reality, to the best of our knowledge, is not addictive. Well, at least so far, we haven't found too many people that are addicted to virtual reality goggles. And so this could be one way to tackle a mental health problem. Not to mention that depression is one of the main problems facing us mentally. Millions of people are afflicted by it. But with full immersion virtual reality, perhaps we'll be able to create a new reality for these individuals to give them hope, to give them a connection to their fellow human being. And so some people think that, yes, maybe it could even affect our mental health. Okay, well, let's move right along to the next listener phone call.
Hello, my name is Andre. I wanted to ask Dr. Kaku, what is the technology or thing that you find promising of the 21st century that you are looking forward to? And I would love to hear more about what you think is the most revolutionary thing that's bound to happen in the next decade. Thank you.
Well, going to the next decade and beyond, I think BrainNet could be a game changer. Now, today we have the Internet, but you can't send emotions, feelings. You can't send how you feel on the Internet. Memories, knowledge, things are private in your brain. But now we're beginning to decode the signals of the brain. And some people think that one day we'll shoot memories on the Internet. Now, in animals, we can already do that. With mice, we've been able to record memories, and these memories can be sent on the Internet. Now we're doing it with monkeys. And after that, perhaps with Alzheimer's patients, so that we can have memories flooding the brain of an Alzheimer's patient, so they don't wander the streets. And beyond that, perhaps entertainment. Think about it. The movies could be replaced by BrainNet. Instead of seeing a blank screen with sound, you'll feel the emotions of the actors. You'll see the memories that they also see. Now, we can't do that yet. In animals, all we can do is send snippets of small memories. But the very fact that we can do that at all is amazing. And so eventually BrainNet may replace the Internet and also entertainment. Who wants to see TV or radio or television when it's nothing but a blank screen or sound, when you can actually feel what the actors and actresses are feeling? Let's go on to the next listener phone call.
Is a boson made of matter or something non-matter?
You ask a very interesting question that I'm actually working on right now. It turns out that for the past 50 years, we've been smashing atoms apart with our gigantic particle accelerators. And when we smash protons apart, what do we get? More subatomic particles. We get a zoo of them. And we're trying to now categorize and sort them out. We realize now there are two kinds of subatomic particles you get when you blow up a proton. One is the bosons, as you pointed out. They have a spin, and the spin is integer, 0, 1, 2, measured in certain units. But then we have other particles like electrons, protons. They are fermions. They have half-integral spin. And so our bodies are made out of particles that spin, some of them with integer spin, 0, 1, 2, and some with half-integer charge, like a half. Now, why should you care? It turns out there's a symmetry that links the bosons to the fermions, and the symmetry is called supersymmetry. It allows you to mix one with the other. And it turns out that symmetry could be the ultimate symmetry of the universe. It turns out that all known subatomic particles can fit into this new nomenclature of bosons and fermions, giving us the potential of a theory of everything. You see, everything is made out of bosons and fermions. Electrons are fermions. Light is a boson. Everything you see and touch is made out of these two particles, and the symmetry that turns a boson into a fermion is called supersymmetry. And if you want to know more about this, get a copy of my book, Parallel Worlds, which talks about higher dimensions, string theory, the 11th dimension, and the possibility of a theory of everything, which eluded Einstein for the last 30 years of his life. He wanted a single equation that would summarize all known laws of the universe. A single equation perhaps no more than 1 inch long. And that's the goal of supersymmetry. And so when you talk about bosons, you're really talking about the building blocks of reality itself. Okay, let's move right along to the next listener phone call.
Hi, sir. This is Shane Adkins in Myrtle Beach, South Carolina. I'm curious what you think about the Higgs particle and how it relates to the creation of God in the modern time and possibly the death of God in the modern time. Thanks.
Wow. You ask a big question. However, the press has called the Higgs boson the God particle, so I guess it's a fair question. So let me jump right into it. First of all, scientists blow protons apart to find out what matter is made out of. And we found a curious particle that was predicted by the theory called the Higgs boson. And that was the last missing piece of the standard model of particles. So far, looking at the thousands of particles that we've cataloged, we've been able to put most of them into a chart called the standard model. It's a rather ugly theory. In fact, I think it's perhaps the ugliest theory known to science, but it does seem to work. And so the Higgs particle was the last missing piece of the standard model. Now, is the standard model the ultimate theory, the theory of everything? No, it's too ugly. It has 36 quarks. It has 19 free parameters. It has a whole zoo of bosons and fermions. And after the break, we'll say a few things about how all this relates to God and the God particle. This hour is your hour. We were talking about the Higgs boson, a particle which won the Nobel Prize for several physicists a few years ago. And why call it the God particle? Well, it turns out the man who coined it was Leon Lederman, an acquaintance of mine. He's a Nobel Prize winner. And he wrote a book about the Higgs boson, and his publisher thought the book was too boring, and he needed a new title. So the editor went into his grab bag of sensational titles and came up with the God particle. Well, my friend Leon Lederman was horrified, but hey, the editor overruled him, and the name stuck. So you see, it is really a misnomer. The Higgs boson is nothing to do with God. However, you ask a question about God, and it's a fair question. First of all, Einstein was asked about God repeatedly, and he said there are really two kinds of God in his question. In his mind, there's the personal God, the God that you pray to, the God that smites the Philistines, the God that grants your prayers. He didn't believe in a personal God because the universe is so grand, it's so great. Why would the universe care whether or not you get a bicycle for Christmas just because you pray to God for that bicycle? Einstein believed in a different God, and that is the God of order, the God of harmony, the God of beauty. He thought the universe was so grand, so incredible, that it could not have been an accident. And he considered himself to be like a little boy walking into this gigantic library. And all he could do was take out the first book in this library, read chapter 1. And that was the state of modern science, reading the first page of chapter 1, when there's an entire library ahead of you. Now, Galileo was also asked the very same question, and he said that, well, you see, science has a purpose. The purpose of science is to determine how the heavens go. But religion has another purpose, and that is to determine how to go to heaven. So in other words, science is about natural law. Religion is about ethics, how to be a good person, the golden rule, how to be part of the community of humanity, how to love your neighbor. And he thought there was no conflict between the two. The problem, Galileo thought, was when a natural scientist begins to pontificate about ethics, or when a religious person begins to pontificate about natural law. So as long as you keep the two distinct, there's no problem at all. Okay, let's move right along to the next listener phone call.
Hi, my name is Ryan Lasso. I'm in Seattle, Washington. I'm trying to find out what your thoughts are on Alcubierre's warp theories and how they apply to what we're doing with quantum physics and string theory, and if we could ever possibly achieve faster than light travel. Thanks.
Well, you ask a question which is at the cutting edge of modern physics, and that is, can we break the light barrier like they do on Star Trek every night? Is it possible to go faster than the speed of light? Well, Einstein is the cop on the block, but Einstein himself left a loophole, and we'll talk about the loophole after the break. Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, hey, we're talking about what's on your mind. Well, let's move right along and take the next listener phone call.
So, I was wondering about the expansion of the universe, and if possibly it's because dark matter itself is using thermal expansion from the heat of the planets and the suns, and maybe that, if we're all just floating in a fluid of space, maybe that's why things are flying apart. But I don't know. My theory is I don't think it's going to fly apart and die off. I feel that if the energy and the heat dissipates, then the dark matter will shrink back down, just like when metal or liquid or gas cools off. So maybe the universe won't continually expand and go out, but maybe it'll condense back in and perhaps create new energies and new balances. What do you think about that?
Okay, well, let me try to answer the last two questions and in the same breath. The earlier question was about warp drive. And you see, Shakespeare gave us a picture of what the universe looks like when he said that the world is a stage and we are actors and actresses making our entrances and exits on the stage of life. That's a Newtonian view, that space is flat and we are actors walking on the stage of life. Then comes Einstein, who says, not so fast. The stage is warped. Therefore, when you walk on the stage of Shakespeare, it's actually warped, and you feel something pushing you to the left, pushing you to the right, and that's called gravity. Now we realize it could be a trap door in Shakespeare's stage of life. So you can take a shortcut between point A or point B. Then we had Miguel Alcubierre, a physicist in Mexico, an acquaintance of mine, who startled the physics community by saying, well, there's yet another theory of Einstein where the stage of life has a carpet on it, and the carpet is folded up. So you can literally leap distances faster than the speed of light. Let's say you walk across a carpet. Most people walk across the carpet the old-fashioned way, by walking point A from point A to point B. But let's say you have a lasso, and you lasso a table, and you yank the table toward you so that the carpet folds up, crumples up. Then you simply hop across the carpet, and you went from point A to B by taking a shortcut. That's the Alcubierre drive. And how did he get the idea? Believe it or not, he was watching Star Trek. On Star Trek, he noticed that instead of going through a hole, like a wormhole, on Star Trek, they compressed the space in front of you. And he actually found a solution which did that. By compressing the space in front of you and expanding the space behind you, you can go faster than light. But there's a catch. There's always a catch to these warp drives. First of all, you need enormous amounts of energy on the scale of a black hole. And then you need an exotic form of energy called negative energy, which is extremely rare. It does exist. It's extremely rare. And that's the engine that drives the Alcubierre drive. So, sorry about that. We physicists have yet to be able to calculate and be able to produce enough of this negative energy to make warp drive possible. And then the question was, what about dark energy? We'll talk about that after the break. Science Fantastic with Professor Michio Kaku. Well, before the break, we had a question about dark matter. You see, the universe is expanding. And so we were talking about the stage of life, a metaphor given to us by William Shakespeare himself, that we're actors dancing on the stage of life, making our entrances and exits. Einstein says the stage of life can be warped. And that gives us the force of gravity. That's what gravity is. But now we realize the stage of life could have trapdoors. These are called wormholes or shortcuts between point A to point B. But then Alcubierre, a Mexican theoretical physicist, gave us yet another way of going faster than light, and that is by compressing the space in front of you. Now we realize that the stage of life is expanding. So, far beyond the stage of life that Shakespeare envisioned, we now have an expanding stage. And then the question is, what is causing this expansion? We think that there is a new form of energy out there, again, negative energy, and negative matter. And we think that is pushing the stars and pushing the galaxies apart. Now, the caller that called in asked another question. There is this dark matter in the universe. It's invisible, surrounds the galaxy, And we have ample evidence that it really is there, an invisible form of matter that holds the galaxy together. And because it's invisible, it's extremely hard to detect in the laboratory. But you see, when things get hot, they expand. For example, when you ride in a train, have you ever noticed you hear the clickety-clack, clickety-clack, clickety-clack on the train when the train wheels go over the rails? Why? Why do you have that annoying clicking sound? And that is, the rails are not actually touching each other when they lay them down. They're separated by a small gap. Why? Because hot metal expands. And you don't want the rails to expand and warp. You want them to expand so they just barely touch each other. And that's why the rails are separated by a fraction of an inch, and that causes the clicking sound. Another way to see the fact that objects expand when they get hot is if you have a stuck jar. If the lid of a jar is stuck, you run it under hot water. Metal expands faster than glass, and so you can easily then turn the lid of a stuck jar by putting it under water. Also, if you live in a multi-story house, you know that the second floor is hotter than the ground floor. Now, what does this have to do with the question that came in? This person had a novel idea. Maybe dark matter is expanding, pushing the galaxies apart because it's hot. Well, nice try, but it turns out that there's not enough dark matter in the universe to cause the expansion of the universe. You see, dark matter basically surrounds the galaxies. And the galaxies, in turn, are small little dots compared to the enormous size of the universe itself. Nice try. So, and by the way, I should also point out in all fairness that there's a Nobel Prize out there for anyone who could tell us what dark matter is. It's invisible. There's some of it in your body right now. The Earth is moving in a wind of dark matter as it goes around the sun, but it's invisible, extremely hard to detect. It's in your living room, for God's sake. And we're moving in a wind of dark matter. But so far, nobody has been able to show what dark matter is. Now, the leading theory of dark matter comes from string theory. String theory is what I do for a living. In fact, I'm the co-founder of string field theory, one of the main branches of string theory. String theory says that all particles are like resonances in a rubber band. And the more they vibrate, the more particles you get. So what you see around you, the bosons and fermions that you see around you, are nothing but the lowest octave of a vibrating rubber band. Well, the rubber band has higher octaves. And these higher octaves, well, they're invisible. Bingo. We think that is dark matter. And so dark matter, this is mysterious matter that holds the galaxy together, we think is a higher vibration of the string. Now, as a byproduct, it means that every single high school science book has to be rewritten. High school textbooks say that the universe is mainly made out of atoms. Wrong. Sorry about that. It turns out that dark matter is not made out of atoms. It's a new form of matter. The first new form of matter discovered in 2,000 years, ever since the Greeks wondered about atoms. And so we have this mystery. What is dark matter? The leading theory, which is not proven, is that it's a higher octave of a vibrating string. But hey, maybe you have a better idea. And if you have a better idea, then tell me first. We can split the Nobel Prize, you and me, and maybe I'll give you something, because of course it's your idea, maybe I'll give you a subway token for all your effort. Okay, well, let's move right along. I think we have time maybe for one more phone call.
My name is Mark Scher. I hope you can help me. I find it very interesting in the equation that Einstein wrote, E equals mc squared, that light is the factor that allows you to allows you to change from matter to energy. So light must have some intrinsic property that allows it to be the conversion factor. It's got to be more than just the speed, like the serendipity that the speed itself of light causes. There has to be some intrinsic factor involved in light.
Okay, well, we have to wind up. Let me say one more thing, though. It's not that light itself is so magical. The speed of light also applies to gravity. It applies to subatomic particles. So light is not special in terms of E equals mc squared. It turns out that all particles have to obey E equals mc squared, and that gravity also travels at the speed of light. And the speed of light is the upper limit for all subatomic particles, not just light. Well, unfortunately, that's it for Science Fantastic. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries that are revolutionizing our world and touching our lives. And in this hour, we're going to throw the lines open because this hour is your hour. Let's move on now to the next listener phone call.
Hi, Dr. Kaku. My name is Laurel, and I'm from Kannapolis, North Carolina. I'm not sure if this is a particularly good or interesting question, but I've been wondering if, hypothetically, of course, we could locate other dimensions. What sort of system do you imagine we might use to classify and name them? Thank you.
Well, believe it or not, you ask a question that is at the cutting edge of modern physics. We physicists are hot on the trail of a theory of everything, a quest that was initiated by Einstein himself to find a single theory that would allow him to understand all the laws of the universe. The leading theory is string theory, and that's what I do for a living. In fact, I'm the co-founder of string field theory, one of the main branches of string theory. And you may say to yourself, well, smarty pants, if you're so smart, then how come you guys don't win the Nobel Prize for string theory? Well, string theory makes some outrageous statements about reality that have made physicists shake their heads. It has revolutionized the entire field, but it has also created some skeptics as well. String theory is defined not in 3 dimensions, but in 10, maybe even 11-dimensional hyperspace. Now, think about it for a moment. We live in a 3-dimensional world. We can move forward, backward, left, right, up, down. Children know this. You can only move in 3 dimensions. But why 3? Why not 4, 5, 6? Einstein gave us a 4th dimension of time, but what about a 5th dimension? Well, mystics, religious people, theologians, philosophers have often wondered about higher dimensions, dimensions beyond the 3 that we're familiar with. This was once considered the province of crackpots and charlatans and mystics, but now is the province of theoretical physicists who believe that in hyperspace there's enough room to unify all the laws of the universe. You see, in 3 dimensions, the equations that govern protons and neutrons and gravity, they don't fit. They don't fit in 3 dimensions. 3 dimensions is too small to cram the equations of protons and neutrons and electricity and things like that into one framework. However, once you start to add 4, 5, 6 higher dimensions, all of a sudden these other forces meld beautifully into one theory. I have an analogy. Think of flatlanders, people that live on a 2-dimensional sheet of paper thinking that the universe is flat. And the universe started with a crystal, like the Big Bang, a beautiful 3-dimensional crystal that shattered, exploded, and fragments landed on this sheet of paper. Well, the people, the flatlanders, living in 2 dimensions, saw this beautiful object shatter, pieces of it falling in their universe, and they decided to reassemble it. Piece by piece, they put the fragments together. But the final touch, the final unification of all the pieces could not fit in 2 dimensions. Then one day, somebody said, look, if all the pieces of this crystal can fit into 2 gigantic pieces, but these 2 gigantic pieces don't fit together, maybe you can move one of them up into the 3rd dimension, put it on top of the other, and it fits into a perfect diamond. Well, The people there said, well, wait a minute, there is no such thing as a third dimension. There's only two dimensions. In other words, if you add a higher dimension, you can unify symmetries more beautifully than in a lower dimension. Now, the mystics then ask the question, who lives in these higher dimensions? If you are a being living in a higher dimension, you have the power of a ghost, the power of a spirit. For example, if you live in a higher dimension looking down on flat land, and you were to, well, I have to take a short commercial break, but after the break, we'll talk about what you can do if you are a hyper being looking down from a higher dimension, not from the point of view of a mystic, but from the point of view of a physicist. Science Fantastic with Professor Michio Kaku. Just before the break, we had a phone caller who asked about higher dimensions. Now, normally, a scientist would laugh and snicker, and their eyes would sort of roll up into the heavens saying, oh my God, we have a crackpot calling in. Well, we don't think so anymore. Because in physics, string theory is now the dominant theory to take us beyond Einstein. It's the dominant theory which allows us to unify the forces of nature into a single theory. The problem with string theory, though, is not only is it very difficult to test, but it also predicts that 3 dimensions is too small to unify all the laws of nature. We need to have higher dimensions, up to 10, maybe even 11 dimensions, in order to describe our universe. Now, if you are a higher dimensional person, like in 3 dimensions, looking down on flatland only exists in 2 dimensions on a sheet of paper, you would have the power of a ghost. You would have the power of a god. What could you do? First of all, if you draw a square around Flatlander, he is now in jail. Flatlander cannot escape from a square, because no matter where he moves, he bumps into the square. But you can peel him off 2 dimensions, and plop him down someplace else outside the square. So in other words, if you have access to a higher dimension, you can walk through walls. You could disappear and reappear someplace else, and you can walk through walls. Now, 150 years ago, many philosophers and theologians asked a simple question. If science allows for the possibility of a higher dimension, and a higher dimensional person can walk through walls, disappear, and reappear, who has that power? Well, ghosts. And then began a romance with the 4th dimension and ghosts. If you read theological short stories and novels written in that period of time, some of them by H.G. Wells, by the way, the famous science fiction writer, you realize that many of these tales were based on angels and ghosts living in higher dimensions. Now, I'm a physicist. We do not necessarily believe that there are ghosts and angels and demons. However, we do believe that the Big Bang, the origin of the universe, took place in a higher dimension. Now, you may say to yourself, but Einstein gave us a picture that the universe is a bubble of some sort. We live on the skin of the bubble, and the bubble is expanding. Yes, that's called the Big Bang Theory, seen on CBS television every week. The Big Bang Theory says the universe is a bubble, we live on the skin of the bubble, and the bubble's expanding. Now, then the question is, what is a bubble expanding into? If the skin of the bubble is 2-dimensional, and that's all there is, and you were to ask yourself, what is the bubble expanding into? The question makes no sense, because the bubble is the universe. So how can you expand into something beyond the universe? Well, the answer is now obvious. Another dimension. So if you want to know what the universe is expanding into, the answer is hyperspace. So in other words, think of a bubble bath. The bubble bath has many bubbles. Each bubble is 2-dimensional in its surface, but it floats in a higher dimension, the third dimension. And so you now realize that hyperspace could be perhaps the most important advance in all of cosmology, and maybe even theology. Okay, let's move right along now to the next listener phone call.
Hi, this is Mark Scher from Florida. I have another question. My question is, why isn't the universe twice as big as we think it is? If we look in one direction, we're estimating that it's almost 14 billion years old. Why isn't it the same in the opposite direction on the Earth? Thank you very much. I have another question. The standard candle. How do we know exactly that the standard candle is the standard candle? We can look at the Doppler shift and see what it's made out of. And by looking at how much of a shift, we can see how fast it's going and how far it is. But how do we know that all the standard candles burn at the same rate? That's my question. Thanks so much. Bye-bye.
Well, you asked some questions that are really at the forefront of modern cosmology and astronomy. First of all, how do we know how far a star is? Because a bright star that is very far away shines an image which is identical to a dim star which is very close. Well, the way we judge distances is with a standard candle. But we need a standard star. A star that you know is brightness no matter how far it is away. We use variable stars. Cepheid variable stars apparently are all the same throughout the galaxy and throughout the universe. And so when we look at variable stars in other galaxies, these variable stars are very easy to see because they go back and forth in terms of their light intensity. Very easy to see, and we think they're all the same. Therefore, a Cepheid variable that's very bright is obviously very near. A Cepheid variable that is dim is very far away. Now, this gets us into trouble when we talk about distant galaxies billions and billions of light years away. We have to use yet another standard candle. And that standard candle is an exploding star. The type 1a supernova is a supernova that consists of two stars chasing each other, like a dog chasing its tail. One star sucks the lifeblood from the companion star. The original star gets bigger and bigger until it blows up. Now, it turns out that the blowing up process of a star sucking hydrogen from its companion star, we think is the same throughout the universe. How do we know that? Because we understand the laws of atomic physics. The atomic physics of stars eating up other stars is well established. And we know that when a star eats too much of its companion star, it will explode right on schedule. So the type 1a supernova, we think, is the standard candle by which we judge distances to distant galaxies billions of light years from the planet Earth. And then the other question is, how do we know the age of the universe and the size of the universe? Well, how do we know that the universe is expanding at all? We know this because of the redshift. That is, when yellow light moves away from you, yellow light is stretched. When yellow light moves toward you, yellow light is compressed. Now, when you compress yellow light, it turns bluish. When you expand yellow light, it turns reddish. Therefore, we can judge the distance to a star by looking at how red it is. If a star is very red, and it's normally yellow, we know that it's moving very far away. It's moving away from us. If it's blue shifted, we know that it's moving toward us. So we know the velocity using this measure. Distances can be done by using variable stars, and that's how we calculate the fact that the universe is expanding, and we know how far the stars are away. Now, if you look in one direction and you look in the other direction, you see the same thing. So the universe is not double the size, it's really one size. Now, how big is the universe in its entirety? We don't know. This is quite an embarrassment. But it turns out that Einstein's theory leaves open the possibility that the universe could be a gigantic bubble, or it could be a bubble that is so big that it's actually flat and perhaps even infinite. We don't know at the present time. So the leading theory is called inflation. Inflation says that the Big Bang took place much faster than we previously thought. But does inflation give us an infinite universe or a gigantic bubble universe? Sorry about that. We don't know. It's an unresolved question at the present time. Okay, let's move right along to the next listener phone call.
Well, hi, Doctor. My name is Jay Otis. I live in Madison, Wisconsin, in the United States of America. And I just had a question. There's been a lot of speculation that people know the edge of the universe, and I was wondering how is it known how far the universe travels out there, how far it actually goes, and does anyone really know or have any definitive way to measure that as we are finding new kinds of planets and stars and galaxies? I was just curious, is there any way to know how far the edge of the universe is?
Let's take a short commercial break, and after the break, I'll try to answer the question. Is there an edge to the universe? Does it all end someplace? Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Well, before the break, we had a question. What happens when you hit the edge of the universe? I once read a science fiction story where an astronaut went far into outer space until he hit the end of the universe. And sure enough, there was a brick wall out there. And then he looked into the brick wall to see what was beyond. What was beyond the end of the universe? Well, when he came back to Earth, of course, everyone wanted to know what is beyond the edge of the universe. Well, unfortunately, he went insane. He was just spouting gibberish when he came back, and so the answer was still unclarified. What happens if you hit the end of the universe and then see what is beyond the end of the universe? Well, as I mentioned earlier, there are two possibilities. One is that the universe is closed and is a hypersphere. So if you were an ant on a bubble and you were to journey around the bubble, you would eventually wind up where you started from. So in other words, if you have a telescope on a hypersphere and you look at the farthest star in the universe would be our sun. And then what is the farthest object you could see with a telescope in a bubble universe? Well, the farthest object you could see is the back of somebody's head. And that person looks very suspiciously like your back and your head because you're looking at basically yourself. Light has gone completely around the universe, and so your telescope basically photographs the back of your head. Now, that's if the universe is closed and is bubble-like. But as I mentioned, the leading theory of cosmology that fits all the data is inflation. We had the author of the inflation theory on Science Fantastic, Professor Alan Guth of MIT. He may eventually win the Nobel Prize for inflation theory because it does fit all the data. So I asked Alan, well, if inflation theory fits all the data, then is the universe open or closed? And he said it's not clear. The data is not yet good enough for us to resolve the question as to whether or not the universe is really flat and infinite in all directions or just really, really big, giving the appearance that it is flat and infinite when it's actually finite. So sorry about that. The latest evidence and latest data do not conclusively give us an answer, but it does answer one question. How can the universe not have an end? In a bubble universe, the universe is infinite in 3 dimensions. No, 2 dimensions. It's infinite because you keep on going in 2 dimensions, never hit the end. But in 3 dimensions, it's a bubble. It's finite. Okay, let's move on to the next listener phone call.
Dr. Kaku, is there a way to capture carbon in the atmosphere in a meaningful way to change the environment? Thank you.
Well, you ask a question which is at the cutting edge of environmentalists, policymakers, presidents. You're talking about a very crucial question. First of all, the Earth is heating up. Even the so-called skeptics will admit that satellite data taken on the Earth, so on and so forth, all indicate that the Earth is heating up. We can debate as to what is driving it, but after the break, we'll try to answer the question, what do we do about the carbon, which some people implicate in causing the Earth to warm up? Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Where we last left off, we had a call coming in concerning carbon. And that is, first of all, the Earth is heating up. Even the so-called skeptics will admit that. Some people say, therefore, it is carbon which is driving it, giving us global warming. Carbon dioxide in the atmosphere, for example, will allow sunlight to come in and hit the Earth. But once sunlight hits the Earth, it turns into infrared, and infrared cannot bounce back through the atmosphere. It's caught. It's caught. It's a one-way street. So sunlight comes in, but infrared cannot escape, and therefore that causes the Earth to heat up, according to the global warming theory. Now, the question is, if carbon dioxide is implicated, is it possible to sequester carbon dioxide? And the answer is yes. The question is, how economical is it? So here's a strategy. Coal plants are one of the leading creators of carbon dioxide. However, at a coal plant, you can put extra devices which will extract the carbon dioxide and then allow you to bury it. Some people think, therefore, aha, that could be the problem. Such an easy fix. The price of electricity would rise a bit, but it's a small price to pay if you're worried about the heating of the Earth. The key question is cost. Is it cost effective to do that? At the present time, the answer is not clear. There was a major utility which actually put millions of dollars into an experiment to see whether or not one of its coal plants could sequester its carbon dioxide. Unfortunately, the experiment was terminated before conclusion because costs were rising, and that is not a very good sign. And so at the present time, there is no easy way to sequester carbon dioxide. Some people think that ultimately we may have to pass laws to limit it, but as I said before, one quick and dirty way to solve this whole problem is to somehow sequester carbon dioxide cheaply. So if you want to become famous, if you're an inventor out there and you want to become famous, invent some cheap way to separate out carbon dioxide, especially carbon dioxide from a coal plant. Okay, let's move right along to the next listener phone call.
Hi, Michio Kaku. My name is Nick, and this is the question. We know that light acts like a wave in the sense of, or acts like waves in the sense of interfering with other. But my question is it correct to think of light as a wave in the sense that, like in water, it isn't particles moving, but rather energy moving through all of those particles' interactions, so that I'm not being hit by particles shot out from the sun, but simply by the energy carried through all of those potential photons in the path between me and the sun through the electromagnetic. And any photons I perceive were basically already there, hidden in the electromagnetic field, and only became perceivable the moment they jumped up and hit me. Is that a better way to think about it, or is it better to think of it as particles traveling through space, or is that already just a well-known thing and I'm a little far behind? Thank you. Well,
you asked a very embarrassing question that has been the source of a raging debate for over 100 years. For example, many people think that light is a wave, but light will go through a vacuum. But if light goes through a vacuum, then what is waving? A vacuum by definition is nothing. But light can effortlessly go past billions and billions of light years of a vacuum called outer space to reach your eyeball. And every time we photograph a distant galaxy, it means that light can travel through nothing. But if light is a wave, then what is waving? This has caused headaches for 150 years. First of all, Newton introduced the idea that light was a particle. Okay? However, the problem with that idea is that light has wave-like properties. So how can you have wave-like properties and particle-like properties at the same time? Well, Einstein comes along and says that, well, it is possible to do this. Light is made out of photons, but the waves are associated with photons. And that's how you get around it. Well, we'll say a few things more after the break. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Okay, well, during the break, we had a question about light. Is it a particle or wave? And the answer is, believe it or not, it is both. It is a particle, says Isaac Newton. We call it the photon, a particle of light. But as this particle moves, it oscillates. It has an electric and a magnetic field associated with it. And the electric and the magnetic field vibrate as it moves, but it is a particle. Same thing works for electrons. The electron is a particle, but as it moves, it has wave-like properties. But here's where we get into big trouble. What is waving when the electron is a particle? Well, when the photon is a particle, what waves is the electric and the magnetic field. Okay, so it's both a particle and a wave. But the electron has no electric or magnetic field, so what is waving? This gave a headache to Albert Einstein. What is waving if the electron has wave-like properties? And the answer is, it's the probability of finding the electron. At this point, Einstein went nuts. He says, what? That means you cannot tell where the electron is. That means the electron is fuzzy. The electron is not a particle at all. Well, it is a particle, but it has wave-like fuzziness associated with it. In other words, the electron can be two places at the same time. Well, Einstein thought this was nuts. But this is the quantum theory. Sorry about that. Einstein was wrong in this question. The electron is in some place both a wave and a particle, meaning that it can be more than one place at the same time. Now, at this point, if your head starts to hurt, well, join the club. We physicists, 50 years after much of these arguments were settled, we're still pondering the question. How can an electron be two places at the same time? How can you be dead and alive at the same time? These are some of the paradoxes that we call quantum mechanics. And if you don't like it, tough. Get used to it. That's just the way the universe is. Okay, let's move right along now to the next listener phone call.
Assuming that energy can't be destroyed, but only transformed, what happens to the energy of the human body when it dies? Greg King, South Windsor, Connecticut. Thank you.
Well, you ask a question which goes to the heart of theology, biology. It's a question that, ultimately, science does not answer, because science is based on testable, reproducible, and falsifiable experiments. So, some people have tried to weigh the soul. When a person passes away, does something leave the body? Is the body lighter as a consequence of death? Well, people have tried to measure this, and they come up with nothing. That is, the body seems to weigh the same before and after death. So the body does consist of forces. We have electrical forces, which makes our nerves fire. We have chemical forces. We have forces within our DNA molecule. But as far as death is concerned, we scientists, A, have a hard time defining it, and B, a hard time measuring it. Now, this has legal implications, of course, because, of course, doctors and lawyers want to know the time of death. It's kind of fuzzy, because if you define life as the existence of brain and the mental processes, you can have vegetables. That is, the brain is essentially dead, but the body is still alive. And even today, there are questions as to whether or not you are really alive or dead if your brain is dead, but your body seems to be perfectly healthy. And then what happens if the opposite takes place? What happens if your brain is still alive, but your body is more or less dead? And this happens in brain injuries, where the spinal cord, for example, is severed. The brain is perfectly fine, as, for example, the brain of Stephen Hawking, but the body is literally wasting away. And so these are questions that even the law has difficulties answering. But as far as science is concerned, science has a hard time differentiating between life and death in terms of looking at forces which change. We don't see any change in the body when the body dies. Then the next question is, what happens when people come back from the dead? They have near-death experiences. Some people see a light at the end of the tunnel, but that can be duplicated using a centrifuge. The Air Force has actually been able to induce this effect for its pilots by draining blood from the eye as the pilots are in a dive. They will experience the light at the end of the tunnel. Well, unfortunately, this could go on for quite a while as we discuss theological, legal, and biological questions, but we are out of time. Once again, you are listening to Science Fantastic with Professor Michio Kaku.